this technology in their production environment, and one of the most popular containerization tool that exists today is Docker. Hi all, I welcome you to this Docker tutorial session by Edureka, and I shall take this opportunity to explain Docker to you in the most simple way possible without undermining its capabilities. So in this tutorial, we're going to start out by understanding why do we need Docker, what is the requirement of a containerization tool like Docker, followed by what is Docker, in which we shall understand what is Docker, what is it designed to do, along with a very interesting case study on NASA's Land Information System framework using Docker. Next, we're going to take a look at Docker's workflow and architecture. In this section, apart from Docker's workflow, we shall talk about its components, its architecture, Docker Swarm, and Docker Compose. Followed by that, we shall look at the installation and setup of Docker on our Linux machines and a few basic Docker commands. Finally, we shall look at a hands-on session where we're going to see a basic Django app setup created from scratch and deployed with the help of Docker. And then we shall summarize and conclude the session. So since Docker is a containerization platform, it's important to understand what came before containerization, or what is the history of containerization. So before Docker came into the picture, before containerization came into the picture, there was this concept of virtualization, or basically using virtual machines. So virtualization was this technique of importing a guest OS on top of an operating system. And this technique was a revelation at the beginning because it allowed developers to run multiple operating systems in different virtual machines, all running on the same host operating system, which nothing but eliminated the need for extra hardware resources. Now, the advantages of virtual machines or of virtualization are many. Multiple OSs could be run on the same machine. The maintenance and recovery was easy in case of failure conditions. And the third point here being the total cost of ownership was also less due to the reduced need for infrastructure. So as you can see here on your screen right now, you can see that there is a host operating system on which there are multiple guest OSs running, which is nothing but a virtual machine. So as most concepts have their shortcomings, virtualization also had a few. So running multiple virtual machines on the same host OS, each to the performance of degradation. This is because the guest OS running on top of the host OS will have its own kernel, own set of libraries, and own dependencies. And these take up a large chunk of the system resources, that is the hard disk, processor, RAM, and other resources. Another problem with a virtual machine, which used virtualization, that it takes a lot of time to boot up. So the problem is very critical in case of real-time applications, so these drawbacks were always there. Apart from that, you also have the age-old battle between development and production teams, that the code works at development and does not work in productions, because the developer has a system with their own set of libraries, their own kernel, and the apps running on there, whereas the production team has these resources of their own. So this is a problem that you can blame upon the difference in the computing environment. A code that runs on the developer's system might not run on someone else's computer. So this led to a new technique called containerization. Basically, a container brings virtualization to the OS level, while virtualization brings abstraction to the hardware. Containerization brings abstraction to the OS. So what you might notice here is containerization is basically virtualization, but it's more efficient because there is no guest OS here. It utilizes a host's operating system, shares relevant public libraries and resources when needed, and unlike virtual machines, the application-specific libraries and binaries of containers run on the host kernel. So each app has its own set of libraries and binaries in its own little container, which makes processing and execution extremely fast. Even if you have to boost a process, it takes only a fraction of a second, because in case of containerization, all the containers share only the host operating system, but hold all their application-related binaries and libraries in themselves. They are lightweight and faster than virtual machines. So here, as you can see, there is your host OS or your host kernel, which is shared by all the different containers. So the containers themselves only contain the application-specific libraries which are separate for each container. This is what makes them faster, and they do not waste any resource. All these containers are handled by a containerization layer which is not native to the host OS. Hence, a software is needed which can enable you to run containers on your host OS. And this is also how containerization solves the difference in computing environment problem. Now, a developer works on containers instead of virtual machines. The app and its required libraries and binaries all are in one container. So when it is passed on to the testing team or the production team, it does not matter whether their host systems have the same libraries. All the dependencies are already present in the container containing the app. So now that you know what is virtualization and what is containerization, and why do we need containerization, let's move ahead and talk about Docker. Why do we need Docker? So a challenge I briefly spoke about earlier is what I would like to elaborate on in this section. Now, when you have a project code in a development lifecycle, there are different environments. You have your virtual server, you have your staging environment, you have your production environment, you have your QA environment. Now, most of the code that we deploy today is done using VMs or virtual machines. Now, how this works is that a developer or certain developers will write the code, and all of it is placed in a version control system such as Git. Now, this could also be placed in a staging server depending on your organization's infrastructure, but most organizations these days use a version control system. So, more often than not, the code is placed in that version control system. Now, this code is never directly deployed in the production server. It's usually first deployed in a lower lifecycle server like your QA server or your staging server. Now, once it is successful in that, then only it is deployed on your production server. Now, this is where the chances of conflicts increase. So, the same piece of code that might be running on your staging server might not run on your production server. And the reason is very simple, it is the difference in the computational environment. This is also known as infrastructure incompatibility. Now, in most cases, your QA servers or your QA environment, staging environment are always updated. In most organizations, that's the case. It usually has the latest libraries, latest binaries, latest jars, all that jazz. But the same cannot be said for the production environment. So, in order to face all these challenges that is faced, difference in environment and lack of optimization of resources, we use Docker. So this is where Docker comes into picture. Docker does virtualization in the software level, and we call it containerization, as I had mentioned before. So here, as you can see, containers are bundled with their own set of libraries and binaries, but they can communicate with each other with a fixed set of protocols. The thing about containers, however, is that they do not have their own operating systems, which is a great thing, because this is what makes them lightweight and function on very little resources, which makes them really fast as well. So what exactly is Docker? As you can see on your screens, there are two machines. The first one has three software applications. One is Angular based, one is React based, and one is Django based. Now all of them are using common resources from the systems, libraries, RAM, processor, etc. And the frameworks are allocated a location in the memory. Now, how is it different from your machine with Docker? Since you have a Dockerized machine, you have a Dockerized system, all of your frameworks and binaries and libraries required by your Angular app, your React app, and your Django app can be put into their each isolated containers, which are going to run independently from each other without interfering with another app. And the space in which you had your framework stored has opened up. So now you can add another software application there with its own frameworks and libraries, binaries, etc. And that is what Docker is meant to do. It's a tool designed to make it easier for you to create, deploy, and run applications by the usage of containers. Docker is a containerization solution. Docker containers do not use the guest operating system. They use the host operating system, and on top of that host operating system, there is the Docker engine. And with the help of this Docker engine, Docker containers are formed, and these containers have applications running in them. The requirements for those applications, such as all the binaries, libraries, frameworks, jars, etc., are also packaged in the same container. There can be multiple containers running simultaneously. As you can see, there are two containers here in our example, and those containers have applications running in them. And you don't really have to pre-allocate any RAM to those containers. These containers allow a developer to package an application with all its parts, all its needs, and then you can deploy it as one whole package. They are basically lightweight alternatives to virtual machines that use the host operating system. This is basically a general workflow of Docker. So you can see one way of using Docker over here. What is happening is that your developer writes a code and defines an application requirements or the dependencies in an easy to write Docker file. And then this Docker file produces Docker images, so whatever dependencies are required for a particular application is present inside the image. Now, as we have specified many times before, what are Docker containers? Now, the Docker containers we spoke so much about are basically the runtime instances of these Docker images. This particular image is then uploaded onto Docker Hub, from where anyone can pull the image and build a container. Now, Docker Hub is nothing but the GitHub of Docker. It's like a repository for Docker images. It contains public as well as private repositories. So from the public repositories, you can pull your images and you can upload your own images as well to Docker Hub. And then, as I mentioned, from Docker Hub, various teams such as your QA team or production team can pull the images and prepare their own containers, as you can see in the diagram. So this shows a great advantage of Docker is that whatever dependencies that are there that are required for your application to run are present throughout the software delivery lifecycle. If you can recall, the initial problem that was there with VMs was basically that the application worked fine in a development environment, but when it reached the production environment, it was not working properly. So that particular problem is easily resolved with the help of this particular workflow, because you have the same environment throughout the software delivery lifecycle, be it a developer, testing, QA, or production. Now, before moving on to the next section, let's look at a case study about containerizing the NASA Land Information System framework using Docker. Now, developed by the Hydrological Sciences Laboratory at NASA's Goddard Space Flight Center, or GSFC, the Land Information System, or the LIS, is a high-performance software framework for terrestrial hydrology modeling and data assimilation. Basically, the LIS enables integrating satellite and ground-based observational products and advanced modeling algorithms to extract land surface states and fluxes. Now, this framework was very difficult for non-experts to install due to many dependencies on specific versions of the software and compilers. This situation then created a significant barrier to entry for domain scientists interested in using the software for their own computing systems or in the cloud. In addition, the requirement to support multiple runtime environments across the LIS community had created a significant burden on the NASA team. Now, to overcome these challenges, NASA had deployed LIS using Docker containers, which allowed installing an entire software package along with dependencies within a working runtime environment. They also used Docker Swarm, which we shall learn about later, to orchestrate the deployment of the cluster of containers. This installation, that used to take weeks or months, was now completed by NASA officials in minutes, either in the cloud or on premises. Now, moving on, let's look at Docker's workflow and architecture. What you see in front of you is the Docker workflow. Now, the Docker engine uses a client-server architecture, where the Docker engine is simply a Docker application that is installed on your local machine. The client-server architecture communicates using a REST API, and the Docker daemon checks the requests to manage the containers. So the Docker architecture includes a Docker client, which is used to trigger Docker commands, a Docker host which runs the Docker daemons, and a Docker registry which stores the Docker images. The Docker daemon running with the Docker host is responsible for images and containers. We'll understand the concept of images a little later in this very section as a part of Docker components. So to build a Docker image, you can use the CLI or the client to issue a bill to command the Docker daemon which runs on the Docker host. Now the Docker daemon will then build an image based on your inputs and save it in the registry, which can either be the Docker Hub or a local repository. So if we do not want to create an image, then we can just pull an image from the Docker Hub, which would have been built by different users. And finally, if we have to create a running instance of any Docker image, we can issue a run command from the CLI or the client, which will create our Docker container. So this is basically the overall architecture or the overall functioning of the Docker architecture. As we move forward in this section, things will be more clear to you. So as you can see, the heart of the Docker architecture is basically the Docker engine. The Docker engine is simply the Docker application that is installed on the host operating system of your host machine. It works like a client-server application which uses a server, which is a type of long-running program called the daemon process. The second point here is the command line interface or the client. The next component here is the REST API, which is used for communication between the CLI client and the Docker daemon. So now if there is a Linux-based OS and there is one Docker client which can be accessed from the terminal and a Docker host which runs the Docker daemon, we build our Docker images and run our Docker containers by passing the commands from the CLI client to the Docker image. So this was all about Docker engine and its workflow. Now let's talk about the Docker components which you will be most acquainted to hearing. You have your Docker file, which builds into a Docker image, which you run, you get a Docker container, and then you store it in a Docker registry. Let's go ahead and look at all of these components in a little depth, shall we? First of all, you have your Docker file, which is nothing but a text document which contains all of your commands that you as a developer call on the command line to assemble an image. So basically, to create an image, you'll have to write a Docker file and then build it. So Docker file basically has your set of instructions which creates the Docker image. Next, you have the Docker image, which can be compared to a template used to create a Docker container. So Docker images are basically the building blocks of a Docker container. These Docker images are created using the build command, and these are read-only templates. You can then store them, as I had mentioned before, in your Docker Hub or your local registry. Next, after building your Docker image, what you get is a Docker container, and these are read-only templates. You can then go ahead and store them in Docker Hub or your local registry, as I had mentioned before. Docker lets you create and share software through Docker images, and you also don't have to worry about whether your computer can run a software in a Docker image because a Docker container is always there to run it. So in case of Docker images, you can use a ready-made Docker image from the Docker Hub or create a new image as per your own requirements to run in a container. With that, let's move on to the next component, which is a Docker container. So the Docker containers are the ready applications created from Docker images. It's the running instance of a Docker image, and this Docker container holds the entire package needed to run this Docker application. So a Docker container happens to be the ultimate utility of Docker, and hence this is the part of Docker which is most popular and most widely used. So if you talk about the applications, every application is run inside a container. So it is an isolated application platform that contains all you need to run an application built from one or more images. So finally, let's move on to Docker registry, which is a storage component for the Docker images. Now this is where the Docker images are stored, which could either be a user's local repository or a public repository like the Docker Hub, which allows multiple users to collaborate building an application even with multiple teams within the same organization who exchange or share containers by uploading them to the Docker Hub. It helps you control where your images are being stored and integrates your image storage with your in-house development workflow as well. Now, Docker Hub, as I mentioned before, is Docker's very own cloud repository, which is similar to GitHub, which is kind of like GitHub but for Docker images. Hope you guys are with me so far. With this, we have seen the architecture and components of Docker. So now we are going to talk about two other components of Docker, Docker Compose and Docker Swarm. So first of all, let's start with Docker Compose. Now, Docker Compose is a tool for defining and running multi-container Docker applications, which basically means you can run different or multiple containers as a single service. The containers are still isolated, but they can interact with each other using a YAML file, which is used to configure your application services. And then with a single command, Docker Compose up, you can create and start all the services from your configuration. A great example of this would be a microservice such as a shopping app. So for example, you can take any online retail store's app. It could be Amazon, it could be Flipkart, it could be Agio. And the idea behind an app like this is that it's a microservice app, which basically means it has multiple services in one big application. So all of these services individually are easier to build and maintain, and when one service is failing, the entire app is not down. So a retail app like Amazon or Myntra or Flipkart or any app of your choice, it'll have multiple services, like it'll have a login account, it'll have your product catalog service, it'll have a shopping cart service and a checkout service, and this is just the bare minimum. And each of these services could be scaled up or down in their own container, tested and built and fixed in their own isolated containers without interfering with any other service in that entire application. So using something like Docker Compose, you can connect all of these isolated containers as a single service. All right? And the next thing I want to talk about is Docker Swarm. Now, Docker Swarm is a service which allows you to create and manage a group of either physical or virtual machines or nodes and schedule containers. Each of the nodes is a daemon which interacts with others using the Docker API. Docker Swarm is basically a technique to create and maintain a cluster of different Docker engines. Services deployed in any node can be accessed on other nodes in the same cluster. It allows for high availability of services, auto load balancing, decentralization of access, easy upscaling and downscaling of deployments, and rolling updates. So basically how it works is that your manager nodes know the status of all the working nodes in a cluster. Your worker nodes then accept tasks sent from the manager node. There is an agent assigned to every single node to give its task updates to the manager. And finally, the workers communicate with the manager using an API over the HTTP protocol. And that is how a Docker Swarm works. Basically, Docker Swarm is an orchestration management tool that runs on Docker applications. It helps you end users in creating and deploying a cluster of Docker nodes. Each node of a Docker Swarm is a Docker daemon, and all the Docker daemons interact using the Docker API. And each container within the swarm can be deployed and accessed by other nodes of the same cluster. So if you consider an environment having Docker containers, if one of the container fails, we can use the swarm to correct that failure. Docker Swarm can reschedule containers on node failures, and the swarm node also has a backup folder which we can use to restore the data onto a new swarm. So with that, we have come to an end to the workflow and architecture of Docker. So now I'm sure all of you might be eager for actually doing something on Docker. So let's go ahead and install Docker. So here are the steps to install Docker on Ubuntu, on your Linux systems, on your Ubuntu systems. You will be using the command sudo apt install docker.io on your Ubuntu systems to install Docker on your system. So let's go ahead and start up with the installation. Today I am using the Ubuntu distribution running on my Oracle VM VirtualBox. So we're going to start out by updating. So sudo apt update. and this might take a little bit time, so kindly be patient. This is a good practice before making any installations, any setups on your machine. All right. As you can see, all my packages are upgraded, and now we can go ahead and install Docker. So to install Docker, we are going to use the command sudo apt install docker.io and then click on Y. And this is also something which takes up quite a considerable amount of time, depending on the speed of your machine, as well as the speed of your internet, so on and so forth. Now understand, this is just one way of doing this, and this is the method I am most comfortable with, and that's why this is the method I will be demonstrating here. There are 2-3 other methods through which you can download Docker on your machine. And not just in Linux, you can also install Docker Desktop on Windows, just in case you do not want to use a virtual machine. And you can also use a cloud platform such as an EC2 instance to run all of these Docker commands that I shall be showing you later in this session. So now we are going to start and enable Docker using sudo systemctl. Okay, with that we have started and enabled our Docker machines. And now we are going to go ahead and check out our Docker version that's running. And as you can see, this is the Docker version and this is the Docker build that we are running. All right. So moving on, we are going to get to our hands-on section. In this section, we will learn how to create a Django project setup using Docker and deploy it on our local host. For that, remember, you need to have a GitHub account and Docker installed on your machine, just the way I showed you right now. We're going to build a backend REST API with Python and Django. We're going to create a new GitHub project that we are going to use to store the source code for our recipe app API. Now, this is a wonderful way to show the versatility of Docker. Now, I found this project while browsing through GitHub, and I came to a conclusion that this was a wonderful way to show how eclectic, how versatile is Docker as a tool. So the first step would include initializing a new project on GitHub and coming back to your Linux machine and navigating to where you wish to store your API. There, we are going to create our Docker file using an editor. You can obviously use the VI editor or Nano editor if you please. There, using the editor in our working directory, we are going to be creating our Docker file, our requirements file, and our Docker compose file, which is our YAML file. And then we are going to run our app on the terminal. So this is the basic breakdown of how we are going to create our Django project setup using Docker. So let's go on straight to our demo machine and put all of this into action. So we are going to navigate to GitHub and we are going to create a new public project or repository on GitHub. So let's create a new repository and let's call it Docker Demo API app. And in the description, we're just going to write demo app setup. We're going to keep this public and we're going to initialize this with a README file. All right. So let's go ahead and create our repository. So as you can see, this is a blank repository, Docker Demo API app, just the README file there. So here on our repository page, I'm going to click on this green button, code button, and copy the URL from here, from your clone or download option. We're going to copy this to our clipboard so that we can clone this particular repository using our terminal. I'm going to move on to the terminal, and I'm going to load my terminal and navigate to the directory where I want to store my app. So maybe I'll just save it here. I'm just going to clone this repository to my local machine. All right, and that's done. Now you can go ahead and change your directory to the repository. So now I'm going to use the command ls to see if my repository has been cloned. Yes, it has been cloned. You can see the Docker demo API app is cloned right here on my local machine. So I'm going to change my directory to this repository I just created by typing the command cd docker demo API app. Now what I'm going to do is I'm going to open up this project in the editor. Like I had mentioned, you can use any other editor. You can use the VI editor, the Nano editor, any editor that you're comfortable with. So now I'm going to clear all of this. And I'm going to use the Nano editor to create the Docker file first. So just Nano and Docker file. There's no spaces between Docker and file. And I am going to put in this code over here. All right. So this is my Docker file. So the first line of the Docker file is the image that you're going to inherit your Docker file from. With Docker, you can basically build images on top of other images. The benefit of this is that you can find an image that has pretty much everything that you need for your project. So you can just add customized bits that you need just for your specifications. So we are going to create our Docker file from Python 3.7 Alpine image. Now you can find this if you head over to the Docker Hub. You can find a list of available images that you can use to base your project off of. If you search for Python, it'll take you to a list of items where you can choose this one. So we're going to use the 3.7 Alpine image. So what it is that it's basically a lightweight version of Docker, and that's what Alpine means, and it runs Python 3.7. And the next line is optional. It's usually a maintainer line, but it's useful just to know who is maintaining the project. So I'm going to leave that one out, but you can go ahead and put in your maintainer line. You can put your name or your company's name, whatever name you basically use to keep track to show that who is maintaining this Docker image. Next, we are going to set the Python unbuffered environment variable, the way you set unbuffered environment variable. Now, the way you set an environment variable in a Docker build file is that you type env and then the environment variable that you want to set. We're going to set one called Python, and it's got to be in all capitals, unbuffered, and then we're going to set it to 1. So what this does is that it tells Python to run in the unbuffered mode, which is the recommended mode when running Python within Docker containers. The reason for this is that it doesn't allow Python to buffer the outputs. It just prints them directly and then avoids some complications and things like that. So when you're running your Python application, we are going to install our dependencies. We are going to store our dependencies in a requirements.txt list or file, which we are going to create in a moment. So that what we need to do here is we need to copy our requirements.txt file. And what this does is it says copy from the directory adjacent to the Docker file copy. So we're going to copy the requirements.txt file. Further, we're going to copy it on the Docker image, which is what this /requirement.txt file means. Next, we're going to run pip install. our /requirements.txt. So what this does is that it takes the requirements that we have just copied and installs it using pip into your Docker image. Next, we're going to make a directory within our Docker image that we can use to store our application source code. So you have your run mkdir /app all in lowercase. And below that, we are going to type workdir /app. And below that, we are going to type copy./app /app. What this does is it creates an empty folder in our Docker image called /app at this location. And then it switches to that as the default directory. So any application we've run using our Docker container will run starting from this particular location, unless we specify otherwise, of course. Next, what it does is that it copies from our local machine the app folder to the app folder that we have just created on our image. This allows us to take the code that we created in our project here and copy it to our Docker image. So here we have run add user -D and user. And finally, we are going to switch to that user by typing user. Now this might be a little confusing because I've added the username user for our user, but what this command means is that it says add user which creates a user. User -D says create a user that is going to be used for running applications only. So not for basically having a home directory that someone will log in. It's going to be used simply to run our processes from our particular project. Finally, this user switches Docker to the user that we've just created. The reason we do this is for security purposes. If you don't do this, then the image will run our application using the root account, which is not recommended, because that means if someone compromises our application, they can have the root access to the whole image and they can go ahead and do other malicious things. Whereas if you create a separate user just for the application, then that kind of limits the scope that the attacker would have within our Docker container. All right, so we can go ahead and we can save this file and move ahead to creating our requirements file. So this is what your requirements.txt file will look like. It's just 2 lines. In the first line here, we are installing Django. We are using version 2.2.4, which is the latest stable version that I could find. And that's the version that we are going to use for the project. And then type Django > 2.2.4. So basically what it says is that install Django that is equal to or higher than this particular version. And we do this to take the minor version, which is the last number, and make sure that we install the latest available version, because typically it's the version that has the security features and security fixes and things like that. But it typically doesn't have breaking changes, so we can be confident that our application, when we rebuild our Docker image, will have the latest security patches, even if it does not have the latest version. Okay, in the next line, we're going to install the Django REST framework. So we are using 3.9.0. And in the same way, which we did with Django, we're going to make the install one less than 3.10.0 to get the latest version of 3.9, which is whatever is the latest minor version at the time we build our project. So now we're going to go ahead and save this file as well. Now what we're going to do is we're going to go ahead and create an empty directory called app here for our Docker file to call, because when our Docker file will run and it's going to ask for an app folder, we're not going to have one, then we're going to face issues. So now if I do an ls here, you see we have a Docker file, we have our requirements file, and we have our app folder. Now understand why this is required for our Docker file for us to build it now. So now if you try to copy it without the app folder actually existing, it will give you an error. So now we can go ahead and build our Docker image. So we are already at our terminal. If you're not on your terminal, you can load up your terminal. And if you're on Windows, it'll be your command prompt. Let's make sure that you navigate to your project folder, which I am already at. And then I'm going to type docker build dot. Now what that's going to do is that it's going to build whichever Docker file is in the root of our project that we are currently in. The reason we call it Docker file in the first place is because it's the standard convention that Docker uses to identify the Docker file within our project. So we're going to wait for it to complete, and it should be fairly quick because we are using an Alpine image. It's a very lightweight, minimal image that runs Python. That's how we create a Docker file for our project. And go ahead and create our Docker Compose configuration for our project. So we're going to use Docker Compose as a tool to allow us run our Docker image easily from our project location. So it allows us to easily manage the different services that make up for our project. So for example, one service might be the Python application that we run. Another service might be a database, for example. So let's go ahead and create the Docker Compose file for our project. So nano docker compose dot YAML or YML. So this is a YAML file that contains the configuration for all services that make up our project. The first line of the Docker Compose configuration file is the version of Docker Compose that we are going to be writing our file for. So version colon and 3. Next, we define the services that make up our application. Right now, we only need one service for our Python Django application. So services colon, and in the line below, you're going to type app. This is the name of our service. So we are going to call it out, and then we are going to type build, and then context code on context. So what this says is that we are going to have a service called app, and the build section of the configuration we are going to set the context to dot, which is our current directory that we are running Docker Compose from. Next, we're going to type the port configuration. So we're going to type them in open speech marks. 8080 is our host to port 8080 on our image. So we're going to type that. And then we're going to add a volume. The volume allows us to get the updates that we make to our project into our Docker image in real time. So it basically maps a volume from our local machine here into our Docker container while we'll be running our application. Now, this means whenever you change a file or you change something in the project, you will automatically update it in the container. Now, the good part is you don't have to restart Docker to get the changes into effect. So then you have a /app /app. So what this does is it maps the app directory, which we have here in our project. And this it maps to the app directory in our Docker image. Then you have the command to run your application in your Docker container. So just make sure that the indentation is one indent from where your command starts, and then you type the command. So we're going to use to run our application be sh-c. This means we are going to run the command using the shell, the Python manage py run server. Then we're going to run the server on our local host at port 8080. So this will run the Django development server available on all IP addresses that run on the Docker container. And it's going to run on port 8080, which is going to be mapped through the POS configuration on our local machine so we can run our application. So again, we're going to move on to our terminal and build the Docker Compose file. And what this does is it will build our image using the Docker Compose configuration, and this should not take too much time. So if we're going to build our Docker file, So now we're going to add sudo docker compose build. And as you can see, it's successfully built. Clear it out. So now we're going to use Docker Compose to create the project files for our application. And for that, you can either log in as super user or just type sudo. So Django admin.py, we're going to start project. Now, after running the command, you will realize that if you go into your empty app folder, which was the folder that you created initially, and list out, it's not empty anymore. It has another app folder in it, which contains all of our app setup. I will show you. There you go. You have these files, 1, 2, 3, 4, 5 Python files, which is basically your Django app's entire setup, and all of this Docker created and set it up for you. So a teensy little detail, let's just open up our settings.py file, and we're going to go down to allowed hosts, and just in case it's empty between the close brackets, you can go ahead and add your local host or put in the asterisk, which allows all hosts. All right, so I'm just going to do that, and then I'm going to go back. And now all we have to do is deploy the application through your terminal. So we're going to go sudo docker compose up. So now as you can see, your Django application is up and running. And all of this was possible because of Docker. With that, I come to the end of my demonstration. Hope you enjoyed this demonstration. Now it's time for you to go ahead and try this on your own. I shall leave you with that thought. My name is Upasna. Thank you and have a great day.